The idea is to talk about the problem that is one of my favorite problems since my PhD. So talk about a bit of the background and try to convince you that the problem is interesting somehow, and sort of in the end present a particular approach that I had in my PhD thesis that didn't work, but never managed to fix it. So somehow, perhaps one of you can see it through. I don't know. But so what's the problem? Okay, so let's start with this. Oops. So I'll give you. So I'm interested in solving Schrödinger equation. And I give you some initial data. And I want to solve this in Rn. This is supposed to be for, let's fix the variables x and t. Rn cross R. And I give you initial data. And initial data is supposed to be some L2 function. And there is a known estimate for the solution. So you look at the solution, you can always write the solution uxt using functional calculus, it's the standard. There is the Strichartz inequality. That states that if you take p equals 2 plus 4 over the dimension, that's the exponent that just comes out of scaling arguments. We have this estimate here. So you want to compute LP norm of your solution, and you want to bound with the constant to depend only on the dimension. Well, the L2 norm of the initial data. Okay. So this Strichartz inequality states that this inequality is true for some constant.
1 to the power 1/2.
1/2, thanks. Okay. So that's the problem. So that's an inequality that is known. And what's the problem? What's the problem is to guess what the constant is, the best constant. So you can define, say, let's define Cn to be the best constant here, which would be what? Would be the sup of this norm. So say L2 equals 1, and you take LP norm in space and time. Okay, so that would be the Sharp constant. And the question is, there's a bunch of questions you can ask here. The first one is, what is the Sharp constant? So let me enumerate here. Question 1 would be, what's the value of Cn? And which functions extremize inequality? Let's give a name here. Star. And you can ask a bunch of other questions. Once you answered question 1 and question 2, you can ask questions about stability. of the inequality. So if a function is close to extremize the inequality, should this function be close to the set of extremizers?
Is it obvious that extremizer exists here?
It's not obvious. It is for the cases we know. But as far as I know, there are conditional results for the existence of extremizers. Maybe Diogo knows more than me.
They're unconditional.
These are unconditional.
So here they're conditional, for these they're unconditional, but it's a theorem.
So yeah, but then you would like to figure out question 1 and question 2 and question 3. What's the conjecture here? It's the sort of an obvious one, which is Gaussians are the only extremizers. Okay. Of course, you can multiply by complex explanation and these kind of things, but say modulo natural symmetry is the function you're looking for, or something like that. Okay. So what is known, and please correct me because it's been a long time here. I think dimension, if you look at dimension 1 and 2, this was solved for Plosky back in, I think, 2007. So he solved question 1. He didn't, in question 2, sorry. Okay. And these cases are special because when if you plug in d equals 1 and 2, n equals 1 and 2 here, you get this p equals 6 and p equals 4. The even exponents, and you can do a bunch of tricks with that. You can say p equals 6, for instance, in dimension 1. This would be equal to the L2 norm of the cube, and then you can write the cube as convolutions and etc. You can play with that. There's a bunch of work. There are a bunch of alternative proofs for this. I myself have one, but there's a long history here. There's a heat flow arguments and projection arguments and etc. Okay. All right. What about question 3? Well, you can still ask question 3 sort of if without knowing the Gaussians are extremizers. So this was a paper of mine in Giuseppe, which here. So we showed that if the theorem, forget which year, which is if f is close to Gaussian, okay, then star is true. So at least locally, this follows. And it's a bit more than this, actually, because if it's close to Gaussians, not only star is true with the conjectured constant, I should say, of course, that since this is the conjecture, this will imply that Cn has a particular shape. And let's just write it once. So it's a calculation. You do the calculation and you see that if Gaussians are extremizers, constants should be that. So what you can do here, what you can do is you can say you take the difference of this side minus this side, and you show that if f is close to Gaussian, not only this is greater or equal than 0, which proves the inequality, but it's also greater or equal than the distance of f to these Gaussian manifold, let's say. Okay, so that's what we did. In particular, if you just apply this concentration compactness arguments, you can get a global stability for the known cases. So you get global stability for 1 and 2 as well. So that's what we did. So as far as I know, this is the state of the art. Max extremizers exist, but in every dimension, but we don't know what they are. Okay, so the conjecture is open. So this guy is open. Again, if you want to know more about this, I recommend a survey of Oliveira, Silva, and Foskey. Diogo is here. It's a very nice survey about all this thing, the connections with this, with restriction estimates, because you can, well, this is exactly just restriction estimate for the paraboloid, but there's restriction for the sphere, for the cone, for the hyperboloid, and all this stuff, and all the developments in this field. So I do recommend you read this survey of Diogo. But that's sort of what I want to say about this. Okay, so what I want to do now is, present something which is called the lens transform, which it's sort of a lightning in some way. It simplifies this whole thing, and you will see that after you apply this transformation, it's sort of a pseudo-conformal transformation, if you like to say, that's sort of a compactified space. So you change Rn and the bag measure for the Gauss space, and in there, after the transform, the extremizers should be just constant 1. Okay. Sort of thing also happens for instance, for the cone restriction. So this would be paraboloid. For the cone, you have to apply another transformation. It's called the Penrose transform. And as far as I know, for the hyperboloid, it doesn't have one. You can also do Fourier restriction on the sphere, and in the sphere, constants are conjectured to be optimal. So in a way, what you can say is that constants should be optimal everywhere somehow, maybe just after some clever transformation. Okay, so let me talk about lens transform. So there are ways of seeing this. During my PhD, I came up with a way of seeing it, which I think was different from what it was before. People were looking at this only from the PDE point of view. I'm sort of a person that likes, it comes from approximation theory, so I like functions, orthogonal polynomials, spherical harmonics, and etc. So there is a way of seeing this transform from the natural base you can put here, which are the Hermite bases. But let's just write what the transform is. So suppose you have a solution. What you can do is this transformation here. So the lens transform would be this weird transformation. It's big. So the way I do it, I include P as a scaling, but you don't need to. You can remove that scaling if you like. Times a factor which is important. And then times another factor here which is not so important, but I will write it anyways. Okay, so you do that weird transformation. Okay, so you get solution is U, and you define L of U at a point ys, and y here. I shall always put this for a vector. That would be important. You define this transformation, and this is just a Euclidean norm. And what it does, it compactifies space and modulo sort of a change of variables what you have is the following. So lemma 1. L2 in X, this is equal to the sharp constant here, length transform of Y S. I'll rewrite what those measures are in a moment. And here's just length transform at S equals 0.
The exponential is
I tangent of pi S.
and the first term is 1 or I2? So it's an exponential of modulo 1, right? Is it not?
No, so it's 1 minus I pi S.
Okay, 1, okay, that's
Yeah,
1.
it's just to fix the Gaussian in the end.
Okay, okay.
So
Good, yeah.
So you get, so what's, let me define here, so what's gamma here? Gamma is just a normal distribution.
Okay.
And beta here, so this is an X, I should say. This is in the variable S. S was sort of a stand as the new time here.
Y, right?
Y, sorry. And beta is just the indicator of the interval. Minus a half a head. Okay. So you have these new things. So now you're in Gauss space. But if you look at this, you don't know exactly what's going on. I mean, you have defined. Well, you could just complain and say, well, that's just a change of variables. You didn't do nothing here. But yes, you're right. This is just a change of variables. However, what you have to do is how it translates the problem. So what is this operator that shows up here? Okay, and the operator can be, so I have to talk about Hermite function. Sort of to understand what's going on. Okay, so we need to talk about Hermite polynomials. Okay, so there's a choice of normalization here.
Yes. Or is it an arbitrary?
Oh, sorry.
Yes, the P,
Yeah,
length transform.
yeah.
Does that have to be the P of the Strichartz inequality,
It
or
should be there, yes.
so you cannot put a different P and
You can put any P, I mean, you can take a look, it's just scaling in Y. It's the same scaling in the exponential, like dividing by root P.
yes.
So you can remove that. If you remove that P, what turns out is that this, you have to fix this Gaussian in the end. It has to be a P here anyways. So you have a choice. Either you put the P there or you put the P here.
Okay.
So for me, I mean, so that differs from the, I think from the classical, people don't put anything in there. It doesn't depend on P, of course. But then in the end, you end up with the Gauss space, which has a P here and a P here. It will be a different variance. Okay, I like to keep it normal distribution. So it's just a choice. So Hermite polynomials. So so since we're working with the normal, you have to use what they call probabilistic Hermite polynomials. It's the monic Hermite polynomials. And so on there, defined recursively by And they have a standard generate function. Okay, so that's all the information you need. And the init functions would be for a real variable, would be just a standard init function. And then you have to normalize things. Again, it's up to a choice of normalization. I'm working with Fourier transform with the 2 pi, so I have to put it root 4 pi here. So those would be the init functions. And that set here is our orthogonal set. The orthogonal basis of L2 of R. And here, and then what you can do is if you want to do the high dimensional version, you have to take a multi-index alpha, and you define H alpha of X to be H alpha 1 X1 dot dot dot. And then you define the functions the same way. The alpha is always a multi-index. For a vector, as just the product of those. So is a vector, and you put now a Gaussian with the, this is just a real variable. Now you put the Gaussian with the Euclidean norm, and these are init functions, and they form a orthogonal basis as well. The nice thing that happens is the following. So what happens if you start initial data? So suppose I want to solve some H alpha in Rn. Okay. Can you describe solutions? So now, but in a way, I mean, if you can solve for each H alpha, it's this guy here, this bilinear combination is solved for any initial data in L2. Okay? So what's the flow? What's the propagator? How it acts here? And this is sort of the formula that I couldn't find any place, which was what I proved in my PhD thesis. This is very simple. And sort of when it's understood to be a multi-index, this is just a sum of the alpha 1 plus alpha 2 plus alpha 3. But when it's a vector, like x, this is the Euclidean norm. Okay, just to not confuse both norms. So this is just okay. And it continues, of course, and that is just H alpha of x that's it. Find some factor that we don't care, which does not depend on n, and it has modulo 1. Okay. Say this is a level. Okay. So the solution is quite explicit. This is just this factor here in the end is just like exponential of something which is purely complex, and it does not depend on n, which is alpha, sorry, which is the important thing. So when you're doing norms, etc., it comes out. It doesn't see it. Okay. So what happens is if you do lens transform. So this is u of x t. So you can do lens transform on this guy. So let's call this. So if u x t is this guy, then the lens transform of u times y s is something very, very simple. Okay. And the Cn is the conjectured sharp transform, as a sharp constant. So by this lemma here, to prove the conjecture, just need to prove that this operator here on the right is a contraction. It doesn't increase norm. So this is always less or equal than 1. And I'm describing what the operator is. The operator is that. So then we have a proposition. Conjecture. I mean, we give a name to this conjecture. Conjecture what? Conjecture is. Conjecture A holds. If and only if we have the following. The operator, let me define the operator T of, how can I do that? The best way possible would be if and only if. Let me define something first. Then how can I do it?
Basically, with this point of view, the lens transform decouples time and space, right? When you apply it to a single.
Yeah, it decouples time and space.
Yeah.
That's a good point.
Okay, this is your way of doing it.
So now we are in Gauss space, and I can define the operator. This will be Hermite semi-group, let's call it. It's the operator Tz for a given z that takes h alpha of x to z to the alpha h alpha of x. Okay. So then you define your Hermite polynomials and then you extend by linearity to the whole space. So now we have an operator defined on every polynomial. In polynomials are density in L2 in the Gauss space. So this is a well-defined operator that maps L2 to L2 isometrically, for instance. Because if modulo of z is equal to 1, but in principle could be anything. Now I can write the proposition. If and only if you have the following estimate. So now we'll integrate from S1, and here would be Rn. And there's this annoying scaling that we can't avoid. Oh, this is P. if this holds for every polynomial in variables. Yeah. Questions so far? So you have a restatement of the conjecture in terms of an operator which is a composition of a mid semigroup and a scaling. Of course, you can remove that scaling, but that will show up in the Gaussian, so it's, I guess, a matter of flavor. Okay, and where these, so you can perhaps see a problem here. So I'm using z for a variable in a unit circle. However, if you look at here, if s varies from minus a half, which is what I wrote there, this would vary in angle from minus p over 2 to p over 2. So it's not the full circle, okay? But there is a trick here that you can complete. So there is a symmetry. It was funny. Oops. It was funny because I did this and my thesis, and like 2 or 3 years later, Pata discovered the same thing without seeing my thesis, wrote to me, and I said, oh, I did that already. So he found out this thing as well. Like 2 years after. So now it seems something that it can be approached by this adapting hypercontractivity results. Okay? It's a weird kind of problem because the z has modulo 1, okay? But then you have this scaling. Plus, you have an average on the outside. So usually we're just interested in things like that with some variable z, but now you have those things mixing up together. Okay? So what I want to do is, how much time? Is it okay? It's 3:20. 3:20. Okay. How much time I have? It's up to 4. So that's fine. Okay, so I have 40 minutes. Okay. So what I want to do is sort of explain how one can approach that. Okay, so let me prove the case p equals 6, which would be dimension 1. Okay, you can prove it sort of. Welcome to Germany.
So I imagine that if you assume that you are on r to the power 2n and something is holomorphic, would it be simpler?
Yes, so there are cases when you can prove this conjecture in high dimensions. I think it's when you assume some sort of it's subharmonic or something.
Yeah, because then all the theses are...
Yeah. So for some functions you can prove it. For instance, you can also prove that if the function is just a Gaussian times a affine function, you can also prove it. Because scaling and multiplication, the operation of the Hermite operator there, are the same thing for linear function times Gaussian. So you don't see the difference, that's how you can prove it. So how can you do case p equals 6, which dimension 1? It just made it worse. So then it turns out to be something which you can sort of write by hand. So for now on, f will always be a polynomial. Okay, so you are in dimension 1, so you can just write it as a n hn of x. Now you can order to put the indexes here. And so what you can do is you just write what that is. So that would be S1 or that would be what? Sum of an z to the n. Here it would be just root 3 to the 6 gamma x dz. Okay, and then you want to show that this is less or equal than integral of cube. Okay. But then, well, you can write what this is. Is there orthogonal? The norm with this normalization, the norm of this guy, which is n factorial, the norm is squared. So then you just have to write inside. And then what you observe here, you can use orthogonality. Okay, so you do the trick, which is you take everything to power cube. So that would be an L2 norm of this thing cubed. So let me write it like that. So when you take power cube, you just multiply 3 of these things, which turns out to be this. So alpha here is now a vector of 3 entries. A alpha is just A alpha 1, A alpha 2, A alpha 3. Okay, so you just take the product, and Z is the same, so it's just the normal alpha. And this is now a 3-dimensional Gaussian. Okay. But now, once you multiply this out in a product with itself, these are orthogonal. So they will only live when they are equal. So this would be a sum of alpha and betas. So integrated in S1, and then it'll be A alpha, A beta bar, integral in R of 2 of those things. And that's it.
Orthogonality in Z, of course.
Orthogonality in Z.
In S1.
Because when you take Z times Z bar, then you get something like, in your head, you get something like this.
Yes.
And if you integrate in Z, that's 0 unless these two are equal. Okay? But then you can do more. I mean, then you do sort of separate the slices. So you sum from S equals 0 to infinity. And here would be it would be this. Okay, and now you want to show that this is less or equal, and then here you separate again. A alpha squared, alpha factorial, and now I took the cube, used the same definition, and then you write this. Yeah, that's inequality. So now you can test the computer actually. So this is a matrix, and this is forever as this is finite, many symbols that have this, because they're all positive. So you can just plug in a computer, and see if for each s, this quadratic form is less or equal than this. So you can just compute the largest eigenvalue. Right? And then you do it in a computer and you see, well, all the eigenvalues are the same, and they're either 1 or 0.
Integrals on R3.
Yes, the R3 things.
And also the previous line. Yes. The first line is still R. Okay.
That's why we write papers together. Okay, so you can just test on a computer, and when it turns out that this quadratic form is just a projection. It's just like you can write it as a projection, which would depend on S, applied in the vector A, restricted to each slice, so restricted to the alpha equals S, in a product with itself. Okay, and since it's a projection, it's trivial that it follows, but then you have to show it's a projection. Okay, so how do you show it's a projection? That's more complicated, I won't do it here, but the way you show it's a projection, you just write what the operator is, compute it squared, and show it that it's equal to itself. So you have to show that. So this whole thing is what? It's the sum of a bunch of projections. And what you have to do is that you have to show that. And then done. And this is just, so what is this? How do you show that one thing is a projection for every S? You do the clever thing. You show that they're all projections at once. So you show they're all the projections at the same time. So what you do is that you do a generating function for the projections. You get a big operator, and you show that that big operator is a projection, no matter what the parameter of the generating function is. So it means that each coefficient is a projection, which is one matrix. Okay. So there's a way of showing that, and then you're done. But then you can see that the proof is very much dependent on this being even. So if you go to 2 dimensions, you can do, the exponent is now 4. You can do the same thing, so you end up with something in 4 dimensions, similar to this, that you have to show it's a projection. You can show it again. But then, how do you do it in the general case? Okay, it's not clear that you could do the same thing. Maybe by duality you can do a similar thing, I don't know. But the fact that this is essentially follows from one identity. It's a very nice identity for Hermite polynomials, which is the following. Equals m, and you have to write the factors. And this always happens if this is true. So for each m, you make the sum on the right. This equals to that. And essentially why this is a projection. Okay? So you see that there's this root 3 here. So it's like doing that formula for all the y's equal to 1. So then you have to normalize them. Sorry, all the y's equal to 1 over root 3 and m equals 3. And so you have this, and then you can split the root 3 here in things which doesn't depend on the root 3. And that's why you can, it's involved in the proof of showing that this is. So it's essentially an application of this identity. Okay, so but how can you do the general case? And here's a strategy. It's a general case. So that involves what's comes from this Beckner two-point inequality. So let me just tell you how can one do that. So what's the two-point inequality from this perspective is the following. So suppose you consider a measure mu, which is like a sum of two deltas. Okay. And then you consider this operator here, k of z, which is sort of a version of that operator. But it operates only on the things that this measure can see. So this measure can only see linear functions. So let me use the Hermite. It's series of consequences. So you define this guy like that, okay? And there is a way, a procedure of sort of taking the tensor product of these guys and use that as an approximation of this operator. Okay? But then, one thing, it's the problem here. So if you try this approach there, what's the problem? This guy, two-point spaces, don't differentiate. Scaling keeps value steady. And multiplication, which is sending hn to the nh. Because they do the same thing here. The scaling just changed x by lambda x, but the t guy also does the same thing with x. So how do you differentiate that you have two different things? Okay, so if you just apply Beckner's method, what you can end up with is always t. Okay, so what you want is to end up with something which is not t. So that operator there, tz. So let's write it. It's tz composed with the scaling. So let's say tz composed with scaling. Let me call it s lambda. That's the operator you see there. You first apply tz, then you scale the function by √2/p. And that operator is not in the limit of this process that Beckner developed in this thesis. So you need something else. So what I did in my thesis, which I've realized that, well, this is given, if you just write what this operator is in Gauss space, this is given by a Gaussian. So you need a way of approximating any Gaussian kernel. So I give you a Gaussian kernel, and you find a procedure that approximates it. Okay? And there is such a procedure. And let me try to... And that's what I did in my thesis for dimension 1, and you can do it also in high dimensions, but at some point Valentina and I will try to do that. But in the end, in the end, I figured out that you can do in higher dimensions as well. It's sort of an adaptation of the techniques, but I never wrote anything about it because I didn't have any applications. So let me write what the procedure is.
So you can use that multiplication formula only when P is even integer.
The one up there?
Yes.
Yes. Yeah, what I did in my thesis was also, we just ignore that the problem comes from PDEs, just put any exponent there, replace 6 by 2k, and do any dimension with any even exponent. And then what you show is that only when it comes from the Strichartz case, it's bounded, and when it doesn't come, it's unbounded, but you can say how unbounded it is. So you can compute the norm on the space of polynomials of degree at most d, and you can show it grows like with d to the power.
You also get one of these inequalities with these weighted things that Emmanuel did at some point.
Perhaps, yeah. I don't know, perhaps.
Things that the manual get at some point is
We have the same Strichartz inequality for every even exponent, but you don't get an LP norm on the other side, right? It's like this multilinear thing of a weight.
Yeah, maybe. Yes, Beckner asked the same question. I don't know. Okay, so what's the procedure? The procedure is kind of complicated. So what's the goal? The goal is I am in... That's the goal. I am in Gauss space. I have like normal distribution, and I'm given a Gaussian kernel. And the Gaussian kernel should be anything of the sort minus ax x. Only deal with centered Gaussian kernels, but you can do non-centered ones. Plus, and here you have some yes, you have x, and yeah, I better write this way. Okay, with some, I always forget what you should do here. Is this a matrix? Matrix, yes. Something like that. Okay. So A would be a matrix, symmetric, A and B symmetric matrices. And I want it centered, so I would like to remove that matrix here actually, yes, sorry. So this would be just some sort of a weighted. Inner product, okay. So what's the total amount of information there? The total amount of information, this is symmetric, so it's what? N times n plus 1 divided by 2, same here, plus n, so you have this total amount of information, okay? So then you want to come up with a procedure similar to what Beckner did, so that in the end, the resulting operator that you get in the end, the object that you're trying to approximate, is not just their lead semigroup, is any operator that's given by a Gaussian kernel. So here's a schematic. So suppose I'm giving any measure mu. Mu is going to be a probability measure. Think of it as being finite, supported or having all moments finite, okay? That's point one. Then I'm gonna give you an operator which it's defined for polynomials at least. So imagine this as sitting inside L2 of the measure, and that maps to L2 functions. In most cases, it will just be an operator that takes polynomials into polynomials. Okay. And then what you do, you want to normalize. So this measure has to come with a normalization. So normalize. And this is, you can always do that in the end because you have written on the operator enough. Rn. Okay, so it's normalized, so its covariant matrix is identity, okay? You could think, oh, it could be any covariant matrix, but in the end, you have so much freedom here that just by change of variables, you could force it to happen and change the operator you get in the end. Okay, it's sort of like the normalization thing. Either you choose, leave the Gaussian that shows up with the matrix, or normalize it and put everything in the operator. So I'm giving you a probability measure with normalize and an operator. And then you have two things. Let me do a schematic thing. So I want to define a notion of taking K, convolve the K, that still is an operator here, but is sitting inside of the convolution of the measure with itself. Okay? So you take the convolution of the measure with itself, it's another measure in Rn, and you want to define the notion of an operator which convolves with itself, which defines a new space. You could do that generically, so I want to do that with n-fold convolution. So I want to do that. I want to mimic the central limit theorem. I want to do m times. And this would now be m times and m times. Okay. And then I want to say that this guy, which is this new operator, as m goes to infinity, it's converging to something, which will be a Gauss given by a Gaussian curve. Okay. So how do you define this? And if you look what Wegener did, it's exactly what I will write, but it will not look like, but it is. So you start with L2, I will draw a picture. So n-fold convolution, U. And what you can do is you can take a map. And then you just look at the tensor product, m tensor product of the measure. And what is the map? I will call it the plus map. I call it scaling with S. Let me call it, say, sigma. Sigma of f of x1, xn, xm, is this defined as f of the sum of the variables. Okay? So I take a function here, and it doesn't matter in the end because I'm only dealing with polynomials in the end. Okay, so think of polynomials. But I will apply a projection, so it's better to think that it's sitting inside some L2. So you take a function here, polynomial, and just in n variables, and you just create something in n times m variables, which is just to apply the thing in the sum. Okay? Now you apply the tensor product of your operator here, which operates in this space, because you can just define it. So you just apply the tensor product. So apply the operator in each variable separately. Okay? And there is a natural projection here, which I will call L2 sum in the same space. Which is the projection, so we have a function here, and this function here might just depend on the sum of variables. Okay, so you define that subspace, so this would be the subspace of functions inside here, that depend only on the sum of the variables. So they can be written in this form. Okay? And so in the subspace of this, you can just put the same norm here, induced, and you have projection. Okay? But this is naturally identified with this n-fold convolution of mu with itself. Because functions that depend only on the sum, once you integrate, it's exactly the same by definition as integration against the n-fold convolution. So that's how we define the n-fold convolution. So I'm sort of using the same thing. Let's put it tilde here, just to use this identification. So any function here that depends on the sum of the variables L2 in this space, you just take the f that represents it like that. This f is sitting here and vice versa. Any f that's sitting here, you can extend by this map here. The norms are the same, so this is isometric, isomorphic identification. I'm going to use the same p here to denote this. Okay, so then the operator is this guy here. K convolution with K, which I shall define as Km, is just this guy. Okay? So what you're doing is, so take polynomial here, put all the variables, apply the operator in each variable, and just project. Okay? So that defines a new operator from this space to this space. Okay. That's what Beckner was doing. It doesn't look like what it was. And
so for the kind of K that Beckner had, did you really need the projection, or were you already inside L2 sum?
yeah, you could work, I mean, this step here is sort of a matter of taste, because in the end things will converge by duality, and so you can always just live in here as tensor products in the end, but you could do the projection and actually create a guy here. In the end, doesn't matter.
But I was thinking about the previous step. So if K was just TZ,
Yeah.
the image of the tensor product of K is still going to be in L2 sum, right, or not?
You say this guy here?
Yeah, so the image is going to be inside L2 sum already, or not?
It's going to be inside the tensor product. I mean, tensor operator is in L2.
Okay, so it's not going to be of the form f of a sum. It's not going to be necessarily this form.
Not necessarily here. And yes, this operator is just the standard tensor product of the operator with itself. But the K has to be applied only on things that depend on the sum. And then you project again. Okay? So what's the theorem?
That's what Beckman did. No?
What?
It's exactly the same thing as Beckman. No? This definition, identification. No?
This identification, yes. It is, yeah, because it depends on the sum, so it depends the combination, yes. But I think he didn't rule exactly like that. But yes. So the theorem is the following. So for each k that you start with, plus, so we'll write in a moment, plus some orthogonality conditions. On k, okay, which I can write in a moment. There will exist a unique Gaussian current. Let's call it G, which would depend on K. such that the limit when m goes to infinity of integral on Rn. So you apply this m convolution, you call this Km. Km, and you have to apply it in the scale function, otherwise it doesn't work. H, the mu, and then this mu is the convolution. Gamma. So you have a sequence of operators in this space. Of course, that I'm working with these measures, which convolve with itself m times. I have to normalize by replacing the variable by square root of mx, so that the central limit theorem, this is converging to normal distribution. But it's just a scaling which I removed, so it's just to any two functions. So here it's this works for any f and for any polynomials. Okay. In the end, we'll work for more functions, but for polynomials is enough. Okay. So indeed, you construct a sequence of operators sitting on sort of the same thing, it's just polynomials, that converges at least weakly to this Gaussian kernel. And the Gaussian kernel is uniquely defined in terms of k. So what is the information needed to write what G is? So if you look here, I need n squared 2n things. And what is the thing in k that's defining G? It is, let me write it here. It is those numbers here. That's the data. The data is so you have n squared numbers here, and you have also k with the function 1. These are the standard base of x, so it's just one image following one variable I. It's the second one, and here's just the first one in the variable j. So here I have n squared information. Here I have n, and you have another one, which is just k of 3j, 2j. And here I have p and more. So bottom line is that it doesn't matter what k does in all the other mid polynomials. It only matters what it does in the first few. This just in each variable actually, separately. Okay. So there is a one-to-one map of this data, and the matrices here, and this vector. It's non-linear map, okay? It's a completely non-linear map from these numbers to this guy, but it's one-to-one, which means it's surjective, sorry. Which means that for any Gaussian kernel, can cook up a huge family of operators that will converge to this Gaussian kernel, okay? And of course, it depends on the measure you start with. It's a balance, it's like a dance between the operator, these numbers, and the measure. Okay, but once you have chosen the correct parameters, you can approximate anything you want. Okay? And so in my thesis, I did the one-dimensional version of this result. And the high-dimensional version I figured out more recently, that sort of follows from the same techniques, but then, and then you can get any Gaussian kernel. So now you have a strategy. 5 minutes. So let me try to show, okay, questions? Okay. So how can we redo the one-dimensional case, p equals 6, with this strategy? That I don't know. If I knew, I maybe would do the other cases. But I have the two-point inequality. So I have first step. Then you just need to prove that you can iterate the process. So what's the problem with what we're doing before? And if you look there, it's not just, okay, of course, a corollary of this thing is if you have a LP, LQ bound of this guy, which is a contraction, then you have an LP, LQ bound of this guy, which is a contraction. So if you start with a contraction, you end up with a contraction. So, and if U is finite, you just have to prove it for M equals 1, because then it will be a contraction for any M. So you just have actually one inequality to show in a finite dimensional space. You just have to cook up the right measure and the right kernel. That could be. So what I wanted to do with this in the end was, the purpose was to give a new proof of Lieb's paper, which is Gaussian kernels have only Gaussian maximizers. But then it sort of became a guessing game, because I have to guess the operator, I have to guess the measure, as the measure with as few points as possible. So it's an easy inequality some way. But that was too difficult, I think. So that's why I never bothered to write anything. But in principle, you could do it. So let me try to, it's 5 minutes to show how you can redo p equals 6 for the base case. And then maybe someone can spot how to iterate this. Okay, so how can we do that? So let me recall you what you would like to redo in the one-dimensional case. So for n equals 1, p equals 6, we want to show that we want to show that, okay? Now with this new strategy, I should throw this up there. How can we do that? So what we need? We need to find a measure, u, and we need to find an operator that satisfies the condition of the theorem. So at least I can approximate the Gaussian kernel that this gives. But now you have a plus thing, which is you can choose the measure. It's any measure. Okay? So let me choose a very particular clever measure, which is this one. So that would be measure mu, 3-point measure. So you can think of a 3-symbol Hamming space, if you like. with these weird probabilities. But what you know about this measure? It's probability. It's 1x and x squared minus 1 are following. And their L2 norms is 1, 1, and square root of 2. Okay, these are the L2 norms of these functions. L2 mu norm. Okay? And why? Because if you go here, yes, let me write here. So the left-hand side here is what? Well, any function here is just anything of the form. It's a three-point space, so this measure only C's to the degree polynomials. I can always assume that A is 1 by scaling, okay? Let's just simplify things. Let's just simplify and assume that that A is 1. And what's the left-hand side now? Is integral in S1, integral on the line of what? 1 plus, and then you have to apply the operator, which is z divided by root 3 bx plus, and this equals z squared x squared over 3 minus 1. Norm 6, the mu is z. Okay. Then you could think, well, let's integrate in z first and enjoy the orthogonality we did before. Wrong. You should integrate in mu first. That simplifies everything. Why? Because I put a 0 right here. Okay? And root 3. So let's just integrate in S1 first. So what you have to do, evaluate this guy at minus root 3. Well, 0 here. Oh, I forgot the c for 0 here. So it's just 1 minus z over z, and it's root 3. So it's just b 6 dz.
Over 6.
Over 1 over 6. But guess what? If I evaluate it plus root 3, I have the same thing with a minus sign, but you're doing modulus, so it's just 2 over 1 over 3. And then you have the other bit, which is 2 over 3, integral of S1. Then you're evaluating a 0. Nice, it's the 0 of this guy. So it's just 1 plus c z squared. And this is just simplified to minus. What a beauty. And this thing, what is this thing here? The right-hand side. Let's write the right-hand side. The right-hand side is just 1 plus b squared plus 2c squared cubed. Because these are orthogonal and these are the norms. But then, well, now I can do orthogonality. I just take the cube here and expand. So it's 1 minus 3 c b squared, no, cb plus 3 cb squared minus cb. I can put a plus here, I don't know why I'm doing that, but anyways. Cube. And similar for the other side. There's a square here. But now z squared, and z cubed, they're orthogonal. So this is just 1/3 of 1 plus, this would be 9 b squared plus 9 b to the 4th plus b to the 6th. And this is just 2/3 of 1 plus 9 c And you can just do it, I mean, this is less simple than that. Then you can just show that. So an inequality is only achieved when B and C are 0. Okay? So we have first step. But we don't have next step. So the next step would be to go to K star. You can do that by hand. I did it in the computer. It works, and you can keep going. It works, but it's getting super complicated. How Beckner avoided doing that? He used that tensorization lemma. If the operator is bounded from LP to LQ, then the tensor is bounded from LP to LQ as well, if Q is greater than P. Okay, so use tensorization. Here you can't use tensorization because you are tensorizing space, so you are tensorizing mu, but you're not tensorizing time. And so in the end, okay, you still get the inequality in the end, but then you have to show it for each step. It's not the case that the first step implies the second. At least I can't see it. But maybe there is some sort of a way of overcoming that. There was, I think, in Epperson paper, for instance, he did something with quaternions to sort of overcome that. They had some issue there. I tried to use that, but I couldn't do it as well. But anyways, if anybody has an idea, please put me as a co-author somehow. But that's it. That's what I want to say.